categorical variables and statistical techniques that we implement when we have categorical variables only. Go ahead and tell you, first of all, there's going to be a situation for R, and we are going to need to install a package called gmodels. And I know it's been a while, so remember what we need to do there is we first need to install packages. And remember, this needs to be in quotes. And the next thing we need to do is access the library. And it doesn't need to be in quotes. So, whether you do that now or, whenever, we're going to need to do that for some of the stuff that we do here. Now, guys, sometimes in research we run into situations where we have categorical variables, and, at the end of the day, I'm not going to sit here and define it for you because I know everyone knows the difference between a categorical variable and a quantitative variable. And but at the end of the day, categorical variables are just grouping variables and describe categories of entities. Okay, hold on. My dog wants out. Wouldn't you know it? Okay, I'm back. Sorry about that. My dog has impeccable timing. It's just like, whatever. Okay, guys. Anyway, the categories just describe, I guess, entities, and they're not test scores or IQs or things that we have quantitative variables that we've seen kind of ad nauseum. We've clearly seen categorical variables before. For example, in the simplest case, we see it in ANOVA because in ANOVA we have a quantitative variable expressed over a categorical variable with more than two groups. If we have just two groups, then we clearly just do a t-test. We've also seen it in standard regression. Now, guys, remember in standard regression, the dependent variable is quantitative, but there's nothing wrong with having categorical predictors. Remember, in standard regression, if we have what I call dichotomous predictors presented as zeros and ones, we can just enter the variable as it is. However, this will be something that we'll revisit quite a bit in 6500. If we have categorical predictors with more than two groups, then we have to create called dummy variables. And dummy variables just, you have to assign a reference group, a comparison group, and then all the comparisons are done with that reference group. Now, guys, a couple things put on the radar. In categorical variables, we have what are called nominal. Pretend that's versus ordinal data. So categorical data breaks down into two different types, nominal data and ordinal data. Ordinal data is just categorical variables that have a natural ordering. You may think of like academic classification, freshman, sophomore, junior, senior. Ordinal data may be the place that you finish in a race, first, second, third, fourth. They're categories, but they have a natural ordering. Nominal data is categorical data that has no natural ordering. Gender, political party, religious affiliation would come to mind for those. Now, some of my buddies and some of my family thinks that political party is a ordinal data because there is a natural ordering, but I disagree. All right, gang, what we want to be able to do is kind of follow out what we do with quantitative variables. So if we want to look at the relationship between two quantitative variables, then we're going to use regression, and more specifically probably look at correlation. If we want to examine the relationship between a student's ACT and their high school GPA, both of these being quantitative variables, then we would use regression techniques and probably even use correlation. However, if we want to look at the relationship between two categorical variables, then or three or four or five, whatever it may be, this is clearly generalizable. Then we have to do different stuff. Okay. Now, what I want to do now is I want to just take a look at a very, very simple case. I want to start out in the simplest way and look at it at a 2x2 table for a couple of categorical variables. Now, what I did is, let's say that we've collected a random sample of n equal 880 adults. And we've asked these people what's their political party, and let's pretend that everybody was either a Democrat or a Republican. And then we also asked them their beliefs about abortion, either pro-life or pro-choice. And let's say that the results turn out this way. Let's say that this is life and this is choice. And this is Democrat, and this is a Republican. So let's keep the numbers just really, really sweet here, and say that the number of Democrats who said that they were pro-life is 150, and the number of Democrats who said they were pro-choice is 400, and let's say there were 250 of these, and let's say there were 80 of these. Now, one of the first things we'd want to do is go ahead and look at row totals and row columns totals. So, guys, we're going to have 550 Democrats, 330 Republicans, 400 who said they're pro-life, and 480 who said that they, let me get over there where you can see that, 480 who said they're, so clearly having 880 subjects, okay? And again, starting this out in the simplest case, where we want to go from here. Well, what we would do in the very simplest case is we would conduct something called a Pearson's Chi-Square test. And Pearson Chi-Square test, what it does is it compares frequencies and counts to what you observe to what you might expect that you would get by chance alone. So we get into these comparing these quantities of what we observe and what we expect to get. And it works a lot like regression. If you think about a residual, it's the observed minus the predicted, right? It's what you saw and what your model predicted. And that's essentially what we're doing here. So you can also think of this right here, the expected as being your model term. So guys, from this, we get what we call a deviation. And the deviation is just the sum of the observed minus the expected, or the predicted, or the model, quantity squared. And guys, again, this is the basis of the sum of squares for regression and for the ANOVA. Now, it has a slight variation to it, and let's talk a little bit about that. Sure, but my computer is really acting kind of strange. It's really kind of hesitating, so don't know what I'm going to do about that. Okay, but guys, has a slight variation, and what we do is in most situations we seek to standardize the deviation, and what we end up doing is we end up creating the Chi-Square Statistic as the sum of the observed minus the expected squared over the expected. So guys, in a nutshell, what we do here is we take a sum of the observed I sub j minus the model I sub j, quantity squared, over the model I sub j. So I would be the ith row, j would be the jth column in our situation, because again, I want to just keep it very, very, very simple. With the initial video would be we would have I equal 2 rows and 2 columns. Okay. Now in ANOVA and regression, we focus on the means, and we look at the deviation around the means. But we can't do that here because we have categories. So we use frequencies and counts instead. So means for ANOVA and regression, but clearly this is not applicable in our situation. So we look at frequencies or counts. Okay, and so we're going to be looking at expected frequencies and observed frequencies and so on and so forth. So that in itself kind of creates a new dilemma, and you think about, well, what's to be expected? And if you think about it, in the situation that we have, where this was, I think, I can't remember now, but was it pro-life or pro-choice? Which one did come first? So pro-life and pro-choice and Democrat and Republican. When we think about under the null hypothesis, which is assuming that there's no, and we're going to talk about this a little bit more in just a second, that there's no relationship between a person's political party and their beliefs on abortion, it makes sense, since we've got 1, 2, 3, 4 possible slots, that we just take 880 divided by 4 and say, well, we expect to get 220 on each of these. But that would be fine if we had the same number of Democrats and Republicans who preferred pro-choice and pro-life. But you can examine the original the data set, and we see that that's not at all the case that we get. So what we want to do here is we want to create expected frequencies in a different way. And the way we do that, and again, this is the model term. Of the EIJ. So what's the expected count, for example, for the 4th row, the 5th column? Well, guys, this turns out it's going to be the row total times the column total. Can you guys see that? Divided by the total sample size. So guys, I'm not going to run through this because this isn't even math, it's just arithmetic. But I'm going to just run through one example. So taking nothing for granted here. So guys, to create the model for life, Democrat, which would be the same thing as creating the expected value for the first row, first column. What we would do is we would take the first row column total. So we have 400 in pro-life. We have 550 Democrats divided by 880. And guys, of my mental arithmetic, let's see, would be equal to 250. All right, guys, so at the end of the day, I just went ahead and did this. So I ask you, which one of those columns do you fit into? I know which one I fit into, but I'm not going to tell you. So 250, 150, 300, and 180. So guys, now what we want to do is we want to compare what we saw and what we should get under random, just by chance. So the Chi-Square Statistic would be calculated by taking the upper left-hand number minus the upper left-hand number. So this part comes from the observed matrix. This comes from the expected matrix. Squared divided by 250, and so on and so forth. Guys, if you do this, you're going to end up with 195.56. Now, this distribution is the Chi-Square Statistic. Follows approximately the Chi-Square distribution with degrees of freedom, the number of rows minus 1 times the number of columns minus 1. So our Chi-Square, because we have 2 rows and 2 columns, our Chi-Square statistic will be modeled by the Chi-Square distribution degrees of freedom equal to 1. Now, that's with R. That's going to be really, really easy to calculate. We would just go. Well, I'll tell you what we'll do. I'm not going to take anything for granted here. Let's just pop over there and see how we would do that. All right, so what I would do here is I would remember that we want the area to the right in the Chi-Square distribution. So I'll tell you what, let me get back over here. So essentially what we want in the Chi-Square distribution, it's going to look something like this, is we want to come to 195.56. And the p-value will be the area to the right of that. Now remember, we're going to use this p-chi command in R, but this is going to give us the area below. So what we're going to have to do is we're going to have to go 1 minus p-chi of 195.56 degree of freedom equal to 1. So let's just pop over there and do that. So 1 minus p-chi of 195. That's extremely large. I just made these numbers up, so that's kind of the reason it happened. Okay, that's cool. Maybe it's Chi-Square. Okay, yeah, it is Chi-Square. So, guys, make that note. And essentially what it's saying, it's not saying that there's no area to the right of 195.56. It's just not measurable according to the calculation methods using R. So, guys, it's highly statistically significant. So, to kind of put this into terms, We always need to be able to determine what's our null and what's our alternative hypothesis. Our null hypothesis would be that there is no relationship or association between political party and abortion beliefs. Nothing like starting the semester out on a controversial issue. Abortion and politics. Man, I tell you what. Okay, hold on. Dogs. At it again. I got to tell you, I'm back. But I got to tell you, I used to, every time Darby would mess up a video, I would start over. And this is the first summer I taught graduate level courses, so I guess it would have been the summer of 2013. And I would start over, and as she's getting older, she's gotten a lot more needy, so I'd never get anything done if I started things over. So the alternative hypothesis is that there is a relationship or association between political party and abortion beliefs. So, guys, we have a p-value that is extremely statistically significant, significant at the 0.001 level. So we reject the null hypothesis and determine that there is a relationship or an association between political party and abortion beliefs. Now, again, guys, you got to remember there's some cool stuff that we're going to get into and how we dive in and actually find out what this means. Because right now you really don't know anything. You probably do know that day in, day out, the Republicans tend to be more pro-life and Democrats tend to be more pro-choice. But let's say you were examining the relationship between two categorical variables that you knew nothing about, and you come up with a statistically significant result indicating that the relationship exists. So, we need more. We need more than just to be able to rely on previous information. So, now, guys, there's a major problem here, and the major problem is the Chi-Square Statistic loosely follows the Chi-Square distribution. Now, if n is extremely large, and the thing about, I can't really give you a definition of what n means to be large because it depends on the context. N being large in regression, n being large in ANOVA, n being large in a chi-square distribution or different things. I think in this situation, chi-square distribution being large is 880 like we have it. So I'm assuming that we have a large sample size here, so our results probably did follow the chi-square distribution okay. But what if we've been doing this on 80 people instead of 880? Well, it turns out that if n is large, there's little difference between the distribution. So the p-value that we calculated is going to be reasonably approximated. However, when n is really small, that's when we end up getting approximations that contain some deviation from the truth, so some bias, if you will. Now, a very naive way to an approach to address this is that we want each expected value count to be above 5. So, in our situation, our expected values were, 250 and 150, and all were clearly above 5. So we had no concern. But there's a lot of times when that's not going to happen. So, guys, if your expected value count of any of the cells is less than 5, then the deviation between the true chi-square, the true p-value and the p-value that you get by using the approximated chi-square distribution can sometimes be quite extreme, and we don't want extreme differences. So at the end of the day, what should we do? And actually that's less than or equal to, right? So what should we do if we come up with an expected cell count less than or equal to 5? Well, a couple things could happen. First of all, we could combine groups. For example, let's say we're running a so let's call this category 1-1, category 1-1, whatever it may be. Yeah. And let's say that we have sufficient expected cell count, but we have an issue right here. What I would probably tell you to do here is to combine the cells. So I would expect you to combine, to take C11 and C21 and then C11 and then add these two together to create a new variable. And we do that a lot in statistics, especially with categorical data like we're examining. Okay. Another alternative to that is the Fisher's exact. Test. So this would be a situation where it doesn't make sense to combine any of the groups, and you could do what's called a Fisher's exact test. And again, Fisher's exact test is typically used when n is small, but the calculations are pretty crazy, so we'll use R a little later to take care of that. Guys, another way to really just an alternate to Pearson's chi-square not sure why my screen isn't going as wide as it used to. So I'll have to work on that before I start the next video. It's what we call the likelihood ratio statistic. And guys, this is based on MLE. You guys remember doing those back in 6,500 maximum likelihood estimation? Well, anyway, I mean, the general idea with MLEs is you collect your data, you create a model for which the probability of obtaining that data is maximized, and then you compare the model to the probability of obtaining the data that you have under the null hypothesis. So again, I wasn't going to write that down, but I think after I went through it, it's probably a good idea. So the general idea, again, of MLEs in general, I'll never be able to repeat this. First thing, collect your data. So the data comes first. The second thing is create a model. And again, the characteristics of the model it's the model which the probability of obtaining that data is maximized. And we, of course, can we saw how we could use calculus to come up with that. And the last part is compare the observed data to the model under the null hypothesis. Now, the likelihood chi-square is found by taking 2 times the sum of the observed component times the natural log of the ratio of the observed component over the model component. So you can see, I think, some similarities, if you stretch the imagination, some similarities between the MLEs that we encountered back in 5500 and what's going on here. So, you know, guys, for our situation, we would have that the likelihood chi-square is equal to 2 times 150 times the natural log of the observed value over the expected value. And you guys can of course handle the rest. I end up getting, I just did this on my calculator before I put up the video. I get 202.58. And if that's not right, don't even let me know about it, because I type this stuff in very quickly. But if you check me, it's off a little bit, then I'm okay with that. I made a typo. But I don't think I made a typo, and I think that would be pretty close. Guys, still follows this likelihood ratio. Test statistics follows approximately the chi-square distribution, degrees of freedom, the number of rows minus 1 times the number of columns minus 1. Now, probably the most important thing that we're going to talk about in this video, other than just getting just a general idea, is you know, of examining categorical data, so we can get into some cooler stuff in the next couple of videos, is the Yates correction. And actually, typically, it's called the Yates continuity correction. And this is one I definitely want you to have on your radar. The reason that the Yates continuity correction model or method is so important is in many 2x2 tables, just like we have. And typically, I never even consider Yates continuity correction unless I have a 2x2 table. What happens is Pearson's chi-square tends to be too small. And what happens in this situation is we get in a situation where we inflate type 1 errors. Now, if you think about it, if if our p-values are lower than they should be, and how can that happen? Well, if you've got a distribution, and let's say the distribution that we think we're drawing from looks like this, and we have a test statistic of any value, and let's just call it the Chi-Square statistic, and this area is over here. But if the true distribution comes in like this, with this being the true p-value, then the one that we get from the distribution that we think we're using right here is going to be too small, right? Well, a too small, because just of the simple characteristic, the simple nature and the definition of a type 1 error. Remember, if H sub O is true or false and we reject or fail to reject, this is a type 1, this is a type 2. We call these smiley faces because that's when the test worked as it should. So if our p-value is smaller than it should be, it's going to lead us to reject a true null more often, which is going to lead us to inflate type 1 errors. So a correction to that is the Yates continuity correction. So I'm going to have just Yates chi-square. And what the Yates does, it actually looks at the absolute value. So it's going to take the sum of, let me get this over here where you can see it, the absolute value of the observed minus the expected minus 0.5 quantity squared. And then it's over the model I sub j. Now, the result is clear. It's going to create a lower test statistic. Hence, it's going to have a lower p-value. So it's going to bring the true p-value down, because of what it's going to do. It's going to look at the deviation, and it's going to. I think I said that wrong. It's going to create a lower test statistic because you're creating you're subtracting 0.5. So a lower value for a test statistic is going to give you a higher p-value, which kind of corrects the natural tendency of the Pearson chi-square to have a lower p-value. So and again, it all comes from that right there. So anyway, you think after you kind of look at this stuff, you think, well, we got it all figured out because Yates continuity correction, and actually then I remember some of the literature saying that that the Yates actually overcorrects. So it actually makes it a little bigger than it actually should be. So these are just things. I had a statistics professor one time tell me that when we're sitting in a stats class, we assume that all these assumptions are just perfect, but out there in the real world, it seems like we're always violating something. All right. Speaking of, well, that was a perfect segue. What are the assumptions of the chi-square model? And this is, whether we're talking about Yates continuity correction, Pearson, Fisher's exact, whatever it may be. Well, some of the usual ones, the usual suspects, normality, equal variances, well, for obvious reasons, those are out of the picture. We don't have quantitative data. But one that's always important is independence. Independence is, without question, the most important assumption for any statistical technique. The other assumption, actually, I take that back. We're doing just strictly greater than, is that the expected values, the model terms, are greater than 5. Okay? So, what I'd like to do now is let's get out of this and jump over into R and see how that's all handled. And there's different ways to do this. We can have our data in Excel and handle it that way as well. But I want to just show you how to take a table like we have and insert the information into R. Guys, remember, first thing we got to do is we've got to install this package. So install gmodels. It'll go through the standard stuff. It's much slower for me because I've got so much running with the on-screen capture device. Well, this is not looking good. There we go. So let's again choose the typical. All right, next thing, library. All right, we're ready to go. Okay, first of all, let's examine this across columns. So I'm going to want to look at the number of Democrats and number of Republicans. So I'm going to call the first Democrat, and looks like we have 150 and 400. And the Republican column, we have 250 for pro-life and 80 for pro-choice. Now what I'm going to call this, we call whatever, let's just call it life. And we're going to bind Dem and Republican. So guys, when you get this, you can see that we have, or at least I hope we do, we have the same thing that we started out with. Now, the next thing is we're just going to run what's called a cross table. And we want Fisher to be true. So we want the Fisher exact result. We want the Chi-Square to be true. We want our expected to be true. I want to include what's called my standardized residuals. I'll explain those in just a second. And I want format to be equal to SPSS. Now, you got two choices there. You can get your format as SAS or SPSS. SPSS will actually give you your standardized residuals. Even though you put standardized residuals right here as being true, it'll calculate those, but it won't show it unless we do format of SPSS. So when we do that, we get a ton of information. But first of all, if we go back to the output, it tells us what what each of these actually are. So let's just focus on the first on this portion right up here. So our cell count of the Democrats who were pro-life were 150. Our expected cell count, our row percentage was 40. Our column percentage was 37.5, and so on and so forth. So the things that are important to me here are the observed count, the expected count, and down here, which is the standardized residual. And I'll explain that in just a second. Now, also, your row total, you can see that 45.5% of the participants were pro-life, 54.5 were pro-choice, 62.5 were Democrat, and 37.5 were Republican. So you get some decent descriptive stuff there. I'm working on a lady on her dissertation. She's actually doing a PhD in mathematics, or in mathematics, a PhD in nursing, and it's little things like this that tend to throw her the biggest curveballs. So guys, come on down, and you can see our Pearson Chi-Square was 195.56, and our p-value is extremely small. The Pearson Chi-Square with the Yates continuity correction. Notice that just as we expected, the test statistic went down, so the p-value went up a little bit. These are such small numbers that going up that much really didn't amount to much. And then we get into Fisher's exact test for count data, and the only thing that we want to worry about right here is the alternative hypothesis where the true odds ratio is not equal to 1. And we're going to learn more about that in videos to come, but you can see that your p-value gives clearly a highly statistically significant result. Okay, so minimum expected frequency is 150. So that just tells us of all the counts up here, of all the cells, that the minimum, and we can see that was pro-life for Republican was 150. At the end of the day, we don't have anything under 5, so we have no reason to have any concerns whatsoever. So, in our 2x2 table, just by eyeballing, it's pretty clear that looking at the percentages, that there's the 45 versus the 28. There's something going on here between Republicans tending to be more pro-life and Republicans being more pro-life and Democrats being more pro-choice. Now again, don't get impatient with me here, because we're building a foundation for cooler stuff. We're just I don't want to build a house on sand and get you into more complicated stuff without making sure that we understand kind of the basics of this. So I guess the next question is, what do we do next when we have a statistically significant chi-square test? So if you want to think of ANOVA, what would we do if we had a statistically significant ANOVA? Well, we would look at post hoc analysis. So anyway, we examine, just like in regression, if the test is statistically significant, we'll examine, just like in regression, the difference between what is observed and what is predicted. But we just call it the difference between what is observed and what is expected, or what is observed in our model. So I'll tell you what, let me get out of this and get back over to where I can do some writing. Guys, we're just about to end this up, so don't lose me just yet. So file this under what we do if the p-value is less than 0.05. Well, what we do is we want to look at the residual for each cell. And this is just taking the observed cell count minus the model cell count. And just like any other residual that we've encountered, if we want to standardize this residual, we're going to take this and divide out by the standard error. Okay? So, what we saw before, it's not the squared deviations as we did with residuals, because we would take the observed minus the predicted and square it. It's just what we call the pure deviation. And divide by the square root of the model. The reason we do that, I think it may be worth talking about. If we have, residuals, and we take the observed minus the predicted, and we square stuff, and the reason we do that is because the sum of the deviations will be equal to 0, and we square these things to keep the sum from being 0. Well, up here we don't care. We're not really worried about the sum of our standardized residuals, because we're just examining each individual cell for its contribution to the overall model. So if we, we can just do this very, very quickly. If we take the first cell count, so let's calculate the standardized residual for Democrat and pro-life. So we're going to have 150 minus 250 over the square root of 250. And I'll tell you what, gang, I don't have a calculator close, so I'm going to leave that one to you guys. But we know what's going on here, because the standardized residual. Let me see if I can make this happen. The standardized residual is given right here. So that value would be negative 6.325. And let me just go ahead and demonstrate that. So if I take 150 minus 250 divided by the square root of 250, we get to negative 6.32, which is exactly what, of course, that we see right here. Okay, gang, what does that tell us? What's that negative 6.32 tell us? Well, that's where this, an understanding of the standardization process, actually, the standardizing process actually comes into to help us here. So reasons. For examining the standardized residuals. First of all, it gives us a component contribution. Which is important in trying to figure out, what component, Democrat pro-life, Democrat pro-choice, Republican pro-life, and so on and so forth, which one has the biggest component contribution in pure deviations, not squared deviations. And the second thing is, and this is, I think, really cool, we can think about this simply as z-scores. And, if you remember back from a 95% confidence interval in the standard normal distribution, the critical values were between negative 1.96 and positive 1.96, telling us if we're testing at 0.05 that the critical values for the test of hypothesis would be, in a two-tailed test, that is, would be the absolute value of 1.96. So what that allows us to do is kind of at the 0.05 level for alpha is it allows us to focus on 1.96, and I usually just kind of keep it simple and focus on 2. So when I'm examining a table like we're given from R, I would go back and look for these values which were higher than 2 or lower than -2. We get a situation here where all 4 are higher than the absolute value of 1.96. And I tell you guys, that's at the end of the day why we had an enormous test statistic. You're not going to see that very often. And what I see here is there's pretty clear-cut relationship between Democrats typically being pro-life. In fact, the percentage is nearly triple. And Republicans being pro-choice, and the percentages are approximately triple. So this is kind of an extreme case that I created just to show you what can happen. And we'll have more subtle cases as we go along. So, guys, that's all I got. This was intended to kind of get the semester started off on a kind of an easy pace, transitioning and get the blood pumping to the brain and that kind of stuff. So, but it'll get cooler in the videos to come. So, guys, take care.